Hello, this is Magic 063 Differentiable Manifolds. I'm Dm Kchm, and this podcast is about the Lie derivative of differential forms. This is a very short podcast. It's just this one frame that's in front of us now, and it belongs with the previous podcast on the various aspects of the Kchm calculus. So this is to do with arbitrary manifolds. There's nothing to do with plus or brackets here. An arbitrary manifold M, and I'm given a vector field, and I'm given a K-form, which could be anything from 0 upwards. And this is the definition. The Lie derivative of omega with respect to x is given by this formula here. And if you look down at the bit lower, I've written out the explicit formula for Lx omega applied to k vector fields y1 up to yk. And it's a good exercise to go from 116 down to this formula here that I've circled. And the first thing that you might want to do is do the case of one forms, which is this formula in the middle. Lx of omega for one form applied to a vector field y is like that. Okay. And strictly speaking, I could write this in terms of angle brackets, and perhaps that would be a good idea. Okay. So, what does it mean? The geometric significance is that this really is a genuine derivative, and for example, if the Lie derivative of omega with respect to x is equal to 0, then omega is constant, and I'll put this in verbal quotation marks, omega is constant in the direction of x. Now that needs a lot more explanation in terms of the concept of flow of a vector field, and we'll get to that later. So at the moment this is a definition that's been more or less pulled out of nowhere, but it is a fundamental identity for Kchm calculus, and the importance of this equation really is independent of the fact that Lx omega is a genuine derivative. Okay, so about Lie derivatives in general, these are differential forms, and of course we've mentioned that the ordinary process of applying a vector field to a function is sometimes called a Lie derivative. It's a very special case, but of course a function is a 0 form, so it is actually a special case of 116 up there. Then it's also true that the Lie bracket of vector fields x and y is a Lie derivative in exactly the same sense, and this notation L sub x of y is often used for the bracket of x and y. And of course that could be the Lie derivative of x with respect to y with a minus sign. The point is that all of these Lie derivatives can be defined in terms of formulas involving the flows of vector fields, and that's what unifies them. So one final comment is that in the light of what I've just said there at the bottom, this formula for the one forms can be written as x. I could write this as a Lie derivative, but I won't. X applied to the smooth function, the pairing of omega with y, minus the pairing of omega with the Lie derivative of y with respect to x. And now you see what I've been able to do in this formula is shift the Lie derivative here of y with respect to x, vector field with respect to x, across to a Lie derivative of omega with respect to x. And that's a general process that we'll get to shortly. Okay, that's all for this podcast.